Hey everybody, welcome back to the Feynman technique. Today I've got an interesting one. This is the integral going from 0 to pi over 2 of the natural log of 2 plus cosine x over 2 over cosine x integrated with respect to x. Alright, so we're going to be using Feynman's technique in combination with an integral formula that I provided in my last video. I will link to that in the description. But to get started, we're just going to do this. We're going to define a new function of t that is equal to the integral from 0 to pi over 2 of the natural log of 1 plus t cosine x over x dx. And we'll notice that if we evaluate f of t at 0, we get 0. Also, if we evaluate our function f of t at the point 1/2, we will end up getting back our original integral. So next, what I'd like to do is take f prime of t, which is just the derivative with respect to t of our original f of t, and then using the Leibniz rule for differentiation under the integral sign, we can get f prime of t is equal to the integral from 0 to pi over 2 of 1 over 1 plus t cosine x. And in a previous video, I derived a bunch of neat trig integrals. And this was one of the formulas that I derived. This right here is true. Obviously, there are certain restrictions on A and B that need to hold, and they're pretty obvious what they need to be. But using this formula, we can see that the integral from 0 to pi over 2 of 1 over 1 plus t cosine x is just this formula where our a is 1 and our b is t. So plugging that in, we see that f prime of t is equal to this. So next, we want to get back to f of t. So all we need to do is integrate f prime of t. Now f prime of t is this, so we integrate it with respect to t. That doesn't look very easy at first glance, and it's not super easy, but here's a little hint. You can make the substitution u is equal to the square root of 1 minus t over 1 plus t. And that's a pretty common substitution for certain forms of integrals. A big clue is that we have that right here, so it kind of jumps out at you. This is what your u is going to be. From there, you can get t is equal to this and dt is equal to this. And then plugging that back into the integral, it actually becomes fairly easy. After simplification, it becomes fairly easy to solve. And you'll see that f of t is equal to negative 2 arctangent squared of the square root of 1 minus t over the square root of 1 plus t. I wrote t plus 1, but same thing. And then plus a constant of integration. So next, we need to solve for our constant of integration. Well, we know that f of 0 is equal to 0. So if we plug in 0 for t, we get negative 2 arctangent squared of 1 plus c. Arctangent 1 is pi over 4, so 2 arctangent squared of 1 is pi squared over 8. So that's what our c is. So we just replace c with pi squared over 8, and that is our new representation for f of t. And now we are done. All we have to do is plug in 1/2 for t, and that is the answer to our integral. And there's some simplification that needs to happen. If you plug in 1/2 for t, obviously this is what you get by just directly substituting it, but that is going to simplify to square root of 3 over 3. And the arctangent of square root of 3 over 3 is pi over 6. So if you create the common denominator and subtract those fractions, you're going to see that our original integral is just 5 pi squared over 72. So there you have it, guys. The integral from 0 to pi over 2 of the natural log of 2 plus cosine x over 2 over cosine x dx is 5 pi squared over 72. All right, guys, hope you enjoyed that, and we'll see you next time.